Super. Hello, everybody. Welcome to today's Delegate Assembly. We're going to have Jeff Carlin talk about a notebook that he's written that uses DP0.2 to explore Milky Way halo science. Let me just share my screen for a moment. So if this is your first time joining us for a delegate assembly, the format's always the same. We start off with some announcements. Today we don't have any announcements. And then we get into a hands-on presentation, so a tutorial where you'll have a notebook and you'll be able to work alongside our presenter. And then at the 10 a.m. point, and this might happen a little bit earlier today or sort of whenever the tutorial is done, we switch over to breakouts. And that's the table that you're seeing at right, a bunch of potential breakout topics where people get together in breakout rooms and discuss some of these. If you're new to Data Preview 0 and it's your first delegate assembly, then you might want to suggest a new delegate co-working. We will go into a breakout room with you, answer any questions that you might have, make sure that you've gotten started okay, that kind of thing. So breakouts can really be anything, right up from I'm totally new here to I want to keep working on this thing that I've been working on for a year. So that's what's going to happen. I think, there we go. So I'm going to kind of hand it over to Jeff. Do you want to take people through how to get a copy of your notebook and then get us started?
Yeah, sure. So this looks like a lot of instructions, but most of it may be familiar to you all from previous delegate assemblies. I suppose the easiest way, if you haven't already in the past cloned the delegate contributions repository, then these are the steps that you would need to go through. So when you're in the, actually here, let's well, no, we won't.
You don't want to share?
Yeah, I could share. I can just do that.
Yeah.
Yeah, I can just demonstrate it. If I can find the window. Oh my goodness. There it is. Okay. Hopefully you all can see a terminal window in the RSP. So if you're in the RSP, you can open a new terminal window. I already have one open here, so I won't do it, but or you can use the big plus to open a new terminal. And then from here, let's say I'm gonna just actually we'll just do it here in my home. All you need to do is clone that repository. So that on the slide there was a oops, oh sorry, I lost my Zoom window. On the slide there was a the path to the repository, and this is just in our Rubin DP0 GitHub repository. But then you just do git clone, and then that path that you can get from going to.
I put the path in the Zoom chat too. It's the whole statement.
Oh, awesome.
Yeah.
Sorry, I need to unfull screen this so that I can see what I'm doing. Yeah, so if you go to the way to find, I'll show you how to find that path in case you forgot. If you go to the Rubin DP0 GitHub repository, then you can click on the delegate contributions DP02. And then from here, if you find the green button that says code and grab this link that shows up here, you can copy it by clicking that. So then if I go back to my window here, I can say git clone and then paste that path. Although that doesn't look right. Okay, did it right. Yeah. And so this will pull down everything in that delegate contributions repository. So when I list everything here, you can see that there's delegate contributions DP0.2 now. And so I can change directory into that and see that there's a whole bunch of stuff, including Milky Way halo density, which is what we're going to look at today. So if I go here to my home folder, you can see delegate contributions DP0.2. I can open that, open Milky Way halo density, and you can see there's a notebook in here. I'll show you also, just for those of you who already have the delegate contributions repo on your in your RSP space. Let me see if I can find it. I'll show you what you can do to just update it in case it's outdated. So here I am in my version of it. And it's not going to show you anything because mine is up to date, but if you type the words git pull from that, it will, if anything has changed since you last updated it, you can git pull. And in my case, it says already up to date because I just updated it yesterday. But that is also the way, if you already had it there, you can update it that way. So I guess before we move on, I want to make sure everybody's.
There is one question. Someone got a permission denied when they did the git clone in the terminal. I've never seen something like that before. I thought you could just always. Oh, unless, so if you were in your tutorial notebooks directory and not in your top level home directory, tutorial notebooks directory is read only. So you would not have been able to git clone into there. So make sure you're in your top level home directory with a CD tilde.
I bet that was the issue. Thanks, Melissa.
Okay, good.
Oh, that was good. That didn't even occur to me. I thought, oh, they could be not a member of the right group or something, but you're totally right. In the tutorial notebooks, if you're in that directory, that's read only. So yeah, good call. Okay, so let me make this so I can see it better. Right, so then hopefully, of course, post in the chat if you have any issues with updating your version of the repository. And this notebook hasn't changed in there for a month or two. So if you've updated it recently, it should be there. But today, basically, the notebook that I'm going to step through, it has very little in the way of like tips and tricks and techniques for how to use Rubin LSST tools. It's more about me wanting to see if we could learn something about the Milky Way as it was simulated in the DP0 data set. And so what we're going to do is use horizontal branch stars. They're turns out easy to pick out in the data preview 0 data set, not so much so in real life necessarily, but in this data set, they're pretty easy to pick out. And the nice thing about horizontal branch stars is they're good sort of standard candles. It's easy to derive their distances. So then we can map out the outer portions of the Milky Way galaxy using these. Okay, so here's what the notebook looks like. For those of you who maybe don't always work on stars in the Milky Way, this you probably remember color magnitude diagram, and this shows you, you see the main sequence. These are for globular clusters, by the way. So this is if all of the stars are at the same distance from us. So you see the main sequence and main sequence turnoff and the red giant branch. And then over here, most Milky Way globular clusters have a really prominent horizontal branch. You can see it in these examples. But those are the stars that we're trying to pick out. And so the first thing you can notice from this color magnitude diagram is that those stars are very blue, which is why we're going to be calling them blue horizontal branch stars. They're very blue relative to all of the main sequence and giant branch stars, which already makes it easier to distinguish them from amongst all of the other stuff. In real life, when you try and select these, there are blue things, very blue objects in the universe, like quasars, white dwarfs, other things that will complicate your selection. But it's a little cleaner in a simulated data set. And also, even in real data sets, you can find ways to select them. And so before we dive into this, I made a quick notebook yesterday just to show. So there you saw color magnitude diagrams of globular clusters. And we're going to use the colors. So we're going to use multiple bands of measurements for these stars to select horizontal branch stars. So I wanted to really quick just show you what color diagrams in a variety of different colors look like in this data set. And so these are objects that are selected, they're known stars because we have the truth table, so we can pick things that we already know are stars. So these are objects that are stars in the DP0 data set. I think this is a 1 degree selection, something like that. And so the black points show all of the objects in the selection, and the red points show just the brightest ones, because those are going to be the more nearby objects. And in fact, most of the nearby objects are going to be more like foreground nearby white dwarfs for the bluest objects. But anyway, I just wanted to create this diagram just so you can see that in these different color spaces, different types of stars occupy different regions. In the G minus R minus I, you can see there's a very clear sequence that most of the stars in the nearby stars land right on this sequence. And then you get over to nearby M dwarf stars, and then they kind of pile up at a given G minus R color. But we're interested in the blue stars, remember? And so you see this extension here where there aren't red dots over the top of it mostly. Those are the blue horizontal branch stars there. You can see it in every panel here. And it's actually a very nice narrow sequence. Again, in real life, it isn't always so narrow and easy to identify. But we're going to take advantage of the fact that we can do that here to think about ways that we could then, in a real data set, identify these things. And so the reason I did the color coding is the red objects are going to be, they're the brightest objects in the sample. And so they might contain some of the really nearby white dwarfs that also have similar colors to horizontal branch stars. And you can see this sequence, this kind of plume that juts out here. Those are likely nearby white dwarfs, while the horizontal branch stars are these guys in the little narrow feature that we want. So just to get you oriented, that's what we're going to be looking at, is these color diagrams, but we're going to be zooming in on just a narrow little piece of this, because we only care about those really blue objects. Okay, so to begin, we're going to import a bunch of packages. Most of these are just some AstroPy and some plotting and NumPy as usual. And then the most important thing RSP wise is getting the TAP service. So we're going to use the TAP service to do a query to get a sample of candidate horizontal branch stars, and then we'll try to whittle that down. So this is just to make plots look nice. So this is just setting the plot defaults. And then this cell is just getting the tap service, initializing the tap service. And so this will show you an example of executing a query. Oh, and it's going to not, here, we'll print that. Right, so here, this shows you the columns that are available in the object table, which is what we're going to use. And so this list has 991 columns. It truncates the list when you print it to the screen, but you can retrieve, if you need to see what's in all of the columns in the table, then you can use this to retrieve that. So in our case, remember, we want to look up objects that have blue colors. So we're going to go G minus R minus 0.3 to 0. If I go back to this guy, you can see we want about, let's say, minus 0.3 to 0. Just to select that range of G minus R. We want to pick stars that are, this is just to, actually, this is probably an unnecessary cut, but I just did G less than 26, just in case there's some stuff that has unrealistic, really faint mags. And then the most important part in the initial query is picking things that are classified as not extended. So you want this ref extendedness is 1 if it is an extended source, or 0 if it's not extended. So I select less than 0.5, gives me things that have been measured as point sources. Okay, and then we're going to select coordinates, UGRIZY magnitudes and their errors using this function that converts flux to magnitude, and those extendedness values, as I said, and then here we use the where clause to say we want the G minus R color to be less than 0, greater than minus 0.3, and you see the ref extendedness less than 0.5. So that's the query that we're going to do. But we can execute this. This doesn't do anything because it's just defining the query. And then when you come down here, this is where you would execute the query. You say service.search query, and it returns this table. I'm not going to do it right now because it takes a long time. So I've already pre-executed it and saved it as a file. I'll show you just when I did this last night. This shows you that it took about 15 minutes to execute that query. So what I did is I execute the query. I then write it out to a FITS file, and that FITS file is in a Scratch space where all of you can access it. So this path, this Scratch Jeff Carlin blah 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 .fits is accessible to all of you. So pretend we waited 15 minutes. We got our query results, and now we have that table, and you can see it has all of those columns that I specified in the query. And in fact, I should show you also, which I didn't here, how many objects did that return? It returned 1.8 million objects. And remember, I didn't specify any spatial constraints. So this is over the entire 300 square degrees of the DP0 data set. Okay, so we're going to try and whittle that down to just a sample of horizontal branch stars. First thing we have to do, since we want to use the colors, we want to have as precise colors as we can. So we're going to correct for extinction. So this is we use this dust maps package, which is already installed when you log into the RSP. And we'll use the extinction values that were derived the DC2 data set in the notebook that's linked here by Sam Schmidt wrote this notebook to derive those coefficients. So these are the coefficients you get. What you get basically is you look up from the Schlegel, Finkbeiner, and Davis maps, you look up a value for this extinction, the reddening in B minus V, and then you have some coefficients that convert to each of the different UG, RI, ZY bands. And so these are the coefficients that were derived in the notebook that I linked here. And then the other thing you need to do is make a sky coord object. This is an AstroPy thing where you give it the RA and the DEC, and you tell it that I want it in degrees in the ICRS frame. And this is just this is what Dust Maps expects as an input. And then we just will use that Dust Maps. Excuse me. We will query the map. So for every star, it will go and look up what the extinction value should be at that position. And then we'll add that. You can see this add column. We'll add that to the table, that EBV value. And this, even for these 1.8 million objects, works really quickly. And then, and here, I'll show you what those look like just for fun. So you can see they're really small values, so we could probably have gotten away without doing these corrections, but we're going to be as precise as possible. Okay, so then we have to apply them. You just correct. So for the U band, it's the measured magnitude minus that ABV times the coefficient, which you remember here. So these are just in order U, G, R, I, Z, Y. And so then all of the ones that have been corrected for extinction are going to have, I just added a 0. So U naught, G naught, et cetera, are the corrected magnitudes. And then just to make it easier, we're just going to pre-calculate all of the colors. So U minus G, U minus I, G minus R, R minus Z, R minus I, and I minus Z. I didn't use the Y band, by the way, for this. Okay, so now we have our data. Let's make some color plots like the ones you saw before, but now remember, we're only in that really narrow minus 0.3 to 0 G minus R color range. And so this will create color diagrams in that narrow range. So again, this is G minus R. You see it's this really narrow range. And this is just showing U minus G, R minus Z, and I minus Z colors on the vertical axis. And so it mostly looks like a big amorphous blob, but you may have noticed there's this little narrow line running through each panel. And that, turns out, is where those blue horizontal branch stars are. Again, in real life, it's never as clean as this. This is a simulated data set, but that's what makes this experiment fairly simple to do.
Hey,
So now oh yeah.
Jeff, what's going on physically with that line?
I think it's just reflecting the how intrinsically narrow the horizontal branch really is in and so it's and I think it's my guess is that that there wasn't any scatter in the simulations. They just simulated I don't know this for sure, but that they were just simulated at a given sequence of temperatures. And so it's I think it's artificially narrow because it's a simulation of without the real scatter of being in a messy galaxy. Like here's an example I'll show you. Sorry, it's a little hard to see. There we go. Here's some data from the Sloan Digital Sky Survey of that. This is that G minus R, U minus G. Oh, except this is, sorry, this is flipped vertically in the U minus G from what you saw over here. So if you take this and you flip it upside down, you can see that swoosh. And then the horizontal branch stars are blueward of that. Where'd it go? There it is. And so this is identifying the horizontal branch stars are even, you can see even in real data, it is a pretty narrow sequence, but I think it's more so in the simulated data because they're just kind of perfect data. But actually, it would be nice to figure out exactly why it's so narrow, Bob. I think that's a good question. But for this, oh, go ahead.
Jeff.
Yeah.
When you're not using the Y band, do they scatter in like Y band colors, or are you just sort of just not using Y band?
I just chose not to because they're intrinsically blue stars, so I just left out the reddest band.
Yeah, okay.
But you could certainly. I actually didn't even explore it, so so it might be fun to an exercise for the for the reader. Yeah, so then this, I'm sure there are better ways to pick out this narrow feature from the data, but I just proceeded in the way that I could think of off the top of my head. And so all I did is, well, before I go on, all I did is I took in each of these panels, I basically just took vertical slices through the data here. And you can imagine when you do that, it should look like, okay, if you started from we'll start from bottom to top. If you'll see it kind of start to rise, and then you'll see a little blip where the narrow feature is, and then maybe it falls, and then you'll see a big peak where all of this is. So the idea is to see that little peak and then identify it at every sort of slice along here, and then we can just fit a line or a polynomial and use that to select. And so there's a lot of that in this notebook. So I might go through it kind of quickly, but yeah, I just bin the data using this 2D histogram and then fit a polynomial to that little narrow feature. Or sorry, I fit a polynomial to the broad feature, subtract it off, and then it should leave the little narrow feature, and use that to identify that, and then fit that locus. So sorry if I explained that poorly. So I fit the broad overall profile, subtract that off. What's left should be this little narrow feature. So we'll try that. And we use 30 bins to do this with the histogram 2D. Okay, so this just does you have that 2D histogram, you just fit the polynomial in each of the slices going across, and then subtract it off. So this is fitting the polynomial and then subtracting it off, and then plotting what's left over. And so now you can see this is in R minus Z color. So this is that vertical axis. You see what's left over in some slices is 0, and then you see this little peak. And so these are the positions that we want to find. So I'm sure, again, there's a better way to do this, but this is what I did. And basically then I said, okay, I can pick out all of those points where it peaks and say those must be that thin feature. And again, it was a really simple way of doing it, but then I can just take the positions of each of those peaks and fit a polynomial to them, and you'll see what it looks like. This is now back in that color space, G minus R, R minus Z. And hey, look, it makes a really nice polynomial curve. So now we could just use that polynomial to pick the objects from that color diagram. And because I wanted it to be better, you can see these are coarse bins so that you get these flat top features. So now I use this as my starting point and did a second round with a finer scale, just to refine it. So you can see here now I used 100 bins instead of 30. But again, you can see the peak picks it out pretty well in almost every slice. oops. And so, but in this case, then when we calculate the residuals, we do it relative to the first polynomial I did. So it makes it easier to pick these out. And then here's what it looks like the second time through. And so now I feel like, okay, I've got that polynomial, I've got that polynomial down for the r minus z versus g minus r. And then we'll just use that later to select things that are near that curve. Okay, and then, and just for fun, you can plot what the coefficients look like of that polynomial. You can see it's a second order polynomial. Where did I specify that? Or sorry, third order. Degree equals 3 was specified in this polynomial fit. So now we have that for the r minus z. I went ahead and did it, and I'll just do this really quick. In I minus z, and again, you can see it picks out the peaks pretty clearly. And then we're going to go through this fast because we'll get back to the fun stuff. And then we refine it. And okay, you always get these outliers, but you can see that the curve is still pretty well defined. Okay, so now we have it for, oh, I think that was I minus z, wasn't it? Or did I mislabel it? I did. Sorry, this is labeled wrong. And then we'll do it one last time for the third panel from that original color plot in the u minus g. And this one's more messy, but you see the first attempt doesn't do a great job. But we're still able to get something that looks fairly reasonable. And by this, you may be looking at it thinking, what do you mean fairly reasonable? Let's demonstrate. Let's actually use these fits and see if we pick things, very near that polynomial in each of those three color plots, does it pick that linear or that narrow feature that we saw in each panel? So for that, we will just use that polynomial and pick things that are within 0.03 mags in the first two and 0.05 because it's a little fluffier in u minus g. We'll just use those as the criteria, and you can set each of these criteria separately, and then you can combine them at the end. But that also means that if you decided you didn't trust one of them, you could remove that selection criterion. So that's what we do here is we evaluate the polynomial fits for each of the three polynomials. And then we say we want it to be within 0.03 mags in the first two, and then in the UG, we want it within 0.05 mags. And then this part just combines all of those separate selection criteria, where you say, okay, I also set an upper limit in the G minus R and a lower limit in G minus R, also I minus Z, and then those separate polynomial criteria. So this just combines all those criteria. So you could imagine if you decided you didn't like the G minus R or I minus Z one, you could ditch that from this if you wanted. So this should combine the selections from all three of those color planes, and then we'll check whether it actually picked things out. So this is the same color diagrams we saw before, but now with the things that we just selected in white. And yay, success. We feel happy about this. With it selected within 0.03 mags in these two and 0.05 in the U minus G. Okay, we've selected that feature. This is great. So now we proceed to doing science with these horizontal branch stars. Of course, I'm assuming they're horizontal branch stars because I kind of know, but I could imagine a person might want to do a little more verification of that fact. But whatever it is, we've selected that feature. We're going to assume they're horizontal branch stars. So now to study the galaxy, the simulated galaxy that these stars are in, we need to know how far away they all are. So to do that, we're going to derive distances, and we're going to cheat a little bit because this relationship that you see here that relates the absolute magnitude in the G band for blue horizontal branch stars to their colors, this was derived from the Sloan Digital Sky Survey. So our measurements are in LSST G minus R colors. So this may not be exactly right, but it should be pretty darn close, like a couple or a few % off. So we're just going to use that. And so we can say, now we know the colors of all the stars. We can get their absolute magnitude, and then by comparing to their measured G-band magnitude, we can get a distance. So I just wrote a little function that you can see. This is that relation from Alice Deason's paper. And then you can see we're just converting from the distance modulus to a distance in kiloparsecs. So that's just a function to do that. And so then we just call that with the G magnitudes, remember, of the selected objects from that selection we developed, and the R magnitudes. And now we have distances, and now we'll turn them into a sky coordinate object again, because sky coordinate objects can contain three-dimensional positions. So you can also, in addition to the RA and DEC, you can give it the distances that we now derived. And then I can convert that into different coordinate frames. And what I am interested in here is relative to the galactic center, because I'm trying to map the structure of the Milky Way. So I want to get the galactocentric coordinates. So once I do this, create the sky coordinate object, then you can use this method that's associated with it to get the galactocentric coordinates. And so now this is just combining in quadrature to get the radial, the radius relative to the galactic center for each of those. So it's just square root of x squared plus y squared plus z squared. And then what I'm trying to extract is, what does the number of horizontal branch stars as a function of radius in the Milky Way look like? Does this simulated Milky Way have a really steep density profile or a really shallow density profile? And that tells us in real life, in the Milky Way, that tells us something about how the halo was formed over time. Like how recently we accreted another bunch of dwarf galaxies, or how distant past that happened, things like that. So so here we just bin up the horizontal branch stars in radial distance from the center of the galaxy. So we say we're going to make bins of 10 kiloparsecs. Oh, and for those of you who aren't used to thinking about the Milky Way should its total extent should be about 300 kiloparsecs, we think. We don't know for sure. LSST will help us determine that. So I'm going to go from 0 to 600 in 10 kiloparsec bins. So we create the bins, and then we just histogram those radii that we measured, and we shift the bin edges by half of the width of the bin, so that the points that we plot will be plotting the center of the bin rather than the edge. That's just a little bookkeeping thing. And then we calculate the volume of the galaxy, because I actually want to calculate the volume density, not just a number density. So now we're thinking about the Milky Way. So in each one of those 10 kiloparsec shells, what's the volume that's contained within that. So then we can get the number divided by the volume. We can get the actual number density as a function of radius. And so, drum roll, what does that look like? This is what we've extracted. So now this is distance from the center of the galaxy, and you can see this goes way out. Remember I said the Milky Way should be like 300 kiloparsecs. And you can see this just continues. Interesting fact. We'll come back to that. And then this is just the density, number density per cubic kiloparsec. And you see it, so it fails nearby because once you get too close, the horizontal branch stars are too bright to be in the data. So that's why it falls off inside about 50 kiloparsecs. But then you see outside of that, it's almost like a perfect power law here. And so then what I am curious about is like, how steep is that power law? Is it falling off like 1/r⁴, 1/r? Let's find out. So we actually then do a fit to that. So as it says here, we're gonna fit a power law of the form rho is proportional to r to the minus n. So n is that power law index. And so we limit that because it sort of breaks down inside about 50 kiloparsecs. We limit it from 70 out to 300, because then you can see it gets noisy out in the outer part. So we'll just fit the part from 300 down to 70 here. And then we just use this function from NumPy called polyfit, and fits a polynomial of order 1, so a line, where we give it the centers of those bins that we plotted above, and then the log of the density. And when we execute that, it says it fit. So this would be the intercept and the slope essentially of that linear fit. We got, this is falling off as a minus 2.7 exponent. And so then we can overplot that, we can just evaluate that polynomial and overplot it. And we can see that it fits really nicely. When you live in a perfect galaxy, you can get really perfect fits, I guess. Essentially, that was the question I set out to ask, is like, can we create something like this by picking out some tracers using the fact that we have a whole bunch of different measurements in a bunch of different bands, so we have multicolor information. Can we pick out a certain type of tracer and then actually fit it recover some information about the Milky Way as it was simulated in the simulated data set? And so we have done that. We have Halo, whose density falls off as about minus 2.7 exponent. For reference, I went and looked. The simulated Milky Way portion of the DC2 data was based on measurements from this paper by Mario Jurich and others from SDSS data. And turns out in that paper, they measured an exponent of 2.8, and we got 2.7. So I feel pretty happy about that. From our simple way of picking things out, we recovered the shape of this halo really well. Yeah, Melissa.
Yeah, I think it's been a while since I used polyfit. Can it give you the uncertainties on your fit parameters?
Oh, that's a really good question. I'm not sure it can. I think you might want to use like SciPy curve fit for that. Let's find out. Oh, you can get the covariances. Okay.
Well, just looking at sort of the scatter in the points, kind of looks like the minus 2.8 would probably be within the error of the fit line, I would guess.
Oh, yeah, totally.
Yeah.
Yeah, that's a good question. I didn't, that could be a good next step, is to try and put errors on that. Because I guess since it's using number counts in each bin, one could calculate just a Poisson error on the number count in each bin and then propagate that through the fitting.
That's exactly what Tom posted in the chat too, that you would have to give it the Poisson errors on your points in order to get the errors on your fit. Okay.
Well, that would be a good exercise, of course, because I couldn't publish it like this because we need some uncertainties on that measurement.
Yeah.
Yeah, thanks for that question. Oh, the other thing that I noted, which I found curious, is that in real life, like, we don't actually know where the edge of the Milky Way is, or if it has an edge. It's probably maybe not a super clear edge, but something like this, if the Milky Way ended at 300 kiloparsecs, you should see this just drop off, and it does not. It seems to continue out all the way to the edge of the data, which I found interesting. So I actually went back to the code that is called code called GalFast that was used to simulate the stars that went into this, and you can actually see a link to the lines in the code itself. Let's do that. The cutoff radius defaults to 1 megaparsec, so 1,000 kiloparsecs. So in fact, sorry, can't get back to my window. So in fact, yeah, this will continue. If the data continued, this would continue all the way out to a megaparsec. So I just I thought that was interesting, and also just to note that if this, we think in real data, once we have LSST data, we should see some kind of truncation happen, and that tells us something about the size of our galaxy. So that's another thing you can do with a study like this. The other thing, one last thing that I tried to do, there are many sort of next steps one could take. One that I think would be really cool would be to try the same thing, but extracting our Lyrae variables, because they're also really good distance indicators, and you could plot the same thing. You could extract a density profile of the Milky Way using RR Lyrae. I'm not an expert in variable stars. I played around with it a little bit, but was not very successful in picking candidates. But I think that would be a fun sort of next step in this. And I think that's all I had to show today. I'm happy to take some questions.
That was excellent. Thank you, Jeff. And I just wanted to start by pointing out that Tom, who is here from the Informatics and Statistics Science Collaboration, has put a reference in the chat about like fitting to power laws. Yeah. So I just wanted to.
That's awesome.
Yeah. Thank you, Tom, for putting that there. Tom, did you want to comment also?
No, nothing. I really enjoyed this. It was really helpful. But that's a good reference. That's kind of the standard reference that people use for fitting power laws.
That's great. Thanks. Maybe I should update this and actually show a more appropriate way of doing it rather than my very simple version.
So then we have one hand up, Jen.
Hi guys. So here, just to get an idea, when can we actually make these determinations? I guess what I'm wondering is like completeness up to a certain magnitude level, right? And then we could actually, based on, do you imagine, Jeff, like we'll have, I guess what I'm asking is, I don't want to wait 10 years to type in all the data. So do you imagine us having like multiple releases and then, where we actually say, okay, hey, here's after X amount of data, we have this amount of confidence, and therefore we can tell the shape out to this, level, the shape of the halo and the distance, associated with L out to this level. Because like, as you mentioned, the RR Lyrae stuff, especially given the new results from the Next Generation Virgo survey. It's kind of cool, right? So that, so yeah, when do you imagine us doing that? And then, of course, subsequent publications from LSST would then say, oh, okay, now we've, to the tails, right? We've addressed these a little bit more with, other data and, have, you see what I mean? Like, I guess what I'm trying to understand is timeline with regard to saying something about the Milky Way. Do you have a feeling on that? Because I know it's kind of a nebulous thing, but a nebulous question. But yeah, do you have a feeling like how many epochs of data or?
That is a very good question, Jen. Thank you. I actually don't know the answer, but we can do a quick thing here where if we plot just the G magnitude, the distance versus G magnitude here, we know roughly in a single visit, the depth, do I remember it in G magnitude? We can do a quick, oops, sorry, when it's in full screen, I can't type. Okay, there. Oh, can I do this quickly? Do I remember where the sort of fact sheet is?
G is, I went to the key numbers. G is
Yeah,
25 for a single.
All right, let's see if we can find it here because since, oh, here it's for scientists.
Yes.
Um,
And then key numbers over at the right.
Key numbers, yeah. So if you ever want to find this, it's on the lsst.org. And then for scientists part, there are key numbers here. Okay, so, right. Point source depth in a single visit in G will reach 25, and then after 10 years, 27. So, so if we go back, this looks like it tells us at 25, we're already well beyond, 700 kiloparsecs just in a single image. So I think the answer to your question, Jen, is like, we could do this with the very first data release.
Exactly. So I know this is more like, this is for planning for our SMWLV, but yeah, I've been thinking about this and, what kind of, publication, type of efforts we could make, first year versus second, third, fourth, that type of stuff. Okay, thanks for just hashing that out with me. Thank you.
Sure. Yeah, that was actually, I'm glad you brought that up because it would be a useful point to make, I guess, in this notebook, that this is what we reach the first time we take an image with this huge telescope. So I guess we would want to confirm that it reaches that depth in all of the bands, but certainly within the first year, we'll have plenty of data.
Exactly. My thoughts, exactly. Thank you.
Yeah, thank you. Were there any other questions or comments? I think I told Melissa yesterday that this was going to be really short, but I guess it wasn't as short as I expected.
It often does take longer to go through the book, and then we slow you down with questions too. So.
Oh, it's fun that way.
Yeah. All right, I don't see any follow-up questions in the chat.
I could think of something if it's, sorry, I didn't raise my hand. Do you think that now, Jeff, that we have this example, and sorry, you guys have provided, the whole team has provided many things for us to work on. If we had like a push, how you mentioned a variety of exercises, should we perhaps write those down and then forward them to the team? And then maybe we could, again, have at another delegate assembly somewhere down a few months down the line. We could also have a Milky Way centered, because I have to admit, I really like this Milky Way local volume centered stuff. And so, yeah, is that something that we could potentially organize?
Absolutely. That's fantastic. And that's partly the reason why we want to have these delegate contribution notebooks, is it's, not necessarily like, hey, I've solved all the problems, check it out. It's a conversation starter. And so, so it really is, let's go take the next step and develop things further. That would be great. And we could, make another, put together eventually another delegate contribution notebook and see where it goes.
I mean, that would be a great breakout room for right now, to just get together, sketch out a couple of things you would want to do in a future notebook, and then, you're started.
Yeah, that sounds great.
Does sound good.